What is calculus? Well, first off, there are two different types of calculus, integral and differential, but this video will only cover differential. Anyways, calculus is a tool that helps us find the instantaneous rate of change of a function, or the IRC, and how it changes. The difference quotient does already help with this, but it takes so damn long and it has so many steps and I hate it. This is where calc, short for calculus if you're new around here, comes in. In this video, I'll be Wait, who the hell is Hatsune Miku? Is what you might be asking. Hatsune Miku, if you don't already know, is essentially the character tied to a voice synthesizer program called Vocaloid. Her voice is just samples taken from a real voice actress, and people use her voice to make music. Her music, and the character as a whole, has been a global sensation. TLDR, the Japanese put a face on an instrument and everyone loves it. So you might be thinking, what the hell does Hatsune Miku have to do with calculus? Well, nothing, actually. But I used desmos to make her out of functions. I put myself through all this work because, 1, it's my final year of high school and I wanted to end it with a cool assignment, and 2, because I take this over writing a formal report any day. I want to get this out of the way first, since piecewise functions aren't exactly a calculus thing, but I learned it in this calc class. And also 90% of this Miku is piecewise functions, so I thought I should at least include this here. I should probably explain this quickly, because it's not actually that important. So, what is a piecewise function? Piecewise functions connect two or more functions by saying, in this domain, the function looks like this, and in that domain, it looks like that. To make this piece of Miku, I connected this function to this function, by only letting this function exist up to the point of intersection, and the second function begins to exist at the POI. You can also make them just not connect, like I did here. Evaluating functions by substituting different values for x is one way to look at a function, but it has one flaw. You can't get an answer at discontinuities, like holes or asymptotes. Rather than evaluating what a function is at a point, limits can help evaluate what a function approaches. This allows us to basically pretend there are no discontinuities in a function, and determine what the function would be at a point without the discontinuity. Let's look at this example. If we want to find the limit of the function at -1, we have to check what it approaches from the positive and the negative sides. Obviously this whole thing would be 1, since it's a constant value. When a limit exists, the function is differentiable at that point. But let's check out this point. This is where the piecewise function connects two different functions, a line and a parabola. You might have already noticed that the function is actually undefined at this point, since if you look carefully at the inequality signs, it's not less than or equal to -0.5. It's just written as less than -0.5. This makes the function undefined at exactly -0.5. Luckily, this isn't a problem for us. If we look at what the function approaches from both sides of -0.5, we can still evaluate the limit as x approaches -0.5. When actually writing this out, you'd use this notation to show that you're looking for a limit. It's the same thing as the difference quotient, just with the limit as x approaches something in front of it. When finding the limit of a piecewise function at a connecting point, you'll want to check the limit of both sides of that point like so. Now we've proven that the limit as x approaches -0.5 is 1. There are also times when limits don't exist. Limits don't exist when the function approaches two different y values. Vertical asymptotes and domain restrictions prevent the limit from existing at the point of discontinuity. Now let's look at x equals 0. The function clearly approaches two different y values here. This means that the function is non-differentiable at this point. Limits can also not exist simply because it's not defined at a point. An example of this is right here, between x equals 0.2 and 0.3. There's nothing written in the piecewise function for the chunk between 0.2 and 0.3, so the function also doesn't exist here. So now we can This part is also simple. We can find the limits of two functions when they look like they're going to approach the same y value and connect them from there. Let's take a look at her face here. I have these three functions that seem to trace her face perfectly, but I need to connect them somehow. I'll do this by finding the limits of these functions at the points where they look like they'll connect. First I gotta connect the white function to the orange one. So I'll check where the two meet and find the limits of each of them at that point. And boom, it looks like they meet there, so I'll join them with a piecewise now. Next I have to do the orange and blue functions. I'll just do the same thing again. And just like that, I can connect all three of them to make one smooth line.
Derivatives? I don't know what that word means. It's such a big word.
Oh my god, that was good. The derivative is just the instantaneous rate of change, or the slope of the tangent line. Taking the derivative has the same purpose as using the difference quotient, but it is so much more efficient with calculus. Finding the slope of the tangent using the difference quotient is called finding the derivative using first principles. You know why? It's because that's the caveman way of doing it. The power rule is really simple. This is what it looks like. There are two steps to doing this. First, multiply the coefficient by the exponent, and then subtract the power by 1. Note that if there are any constants by themselves, like x plus 1, their derivative is 0, as they are not changing. This allows you to completely disregard constants when they're all alone. However, when there's a number multiplying by the function, you keep it there and let it multiply with the derivative. Here's a whole list of derivative rules. There's a lot, and they're not hard, but it'll take too long to cover all of them individually. But I'll also be explaining the product rule, quotient rule, and chain rule. Let's start with a basic example, a cubic function that I used to make Miku's shirt. To take the derivative of this fold, we just have to follow the two steps from before. First, multiply the coefficient, which is negative 100, by the power 3. This will give us negative 300 times x minus 2.41 cubed plus 5.88. So now we're left with negative 300 times x minus 2.41 squared plus 5.88. Again, we can ignore any constants as the rate of change is 0. The complete derivative will be negative 300 times x minus 2.41 squared. This parabola represents the instantaneous rate of change at any given point. When the derivative is positive, that means that the cubic function is increasing. This is called an interval of increase, and the opposite goes for when it's negative. When the derivative is negative, the original function is decreasing, and it's called an interval of decrease. When writing this out, you can use any of these three notations to show that you're taking the derivative. These three all represent the same thing, but they are a little different. When a function is written like y equals this, that's when you use the y with the apostrophe as the derivative. The apostrophe is called prime, so this would be y prime. F prime of x is the same idea. If a function is written as f at x equals this, use f prime of x. Now, dy over dx, or the Leibniz notation, is something completely new, but it's simple. The d's represent small changes in the y and x values. You can use this one whenever you feel like it. This next example might look more complicated at first, but we follow the exact same process. To make this simpler, let's convert the square root into an exponent. Now we do the same thing as before. Multiply the coefficient by the exponent, which will give us 0.65. Next, we reduce the exponent by 1. This will give us negative 1 over 2. And again, we can just get rid of the constant, 5.8. And the derivative will come out to 0.65 times x minus 2.28 to the power of negative 1 over 2. And just like that, we took the derivative of this tiny part of our shirt. If you have two functions multiplying by each other, this is how you would take the derivative of that. F here is the first term, and g is the second term. I'll be taking another piece of Miku for this example. This is another crease in her shirt. The function that I used to make this has two functions multiplying by each other to create the shape. To take the derivative of this, we first have to identify which term is our f and which term is g. F will be the root x minus 2.6, and g is the other one. Now we have to take the derivative of each term. Using the power rule, we can easily take the derivative of both of these functions. Now we have f prime and g prime, and we can just plug all these terms into the formula. And that's our derivative. Here's what it looks like. The quotient rule is pretty much the product rule with one extra step. For this, I'll be using this part of her shirt again. Now we just gotta do the same thing, but with a slightly different formula. So first, we identify f and g, then take the derivatives of each of them. And again, we just plug in each term into the formula to get this. And boom, that's a quotient rule. And this is what the derivative looks like. This one is the most annoying. If you're not organized, it's super easy to mess up, especially on the harder problems. We use the chain rule when we have a function inside another function. This is a good example of this. This shadow in Miku's hair was created using a cubic function inside a fifth root function. To find the derivative of this, we of course have to identify f and g, and then take the derivative of f. F will always be the outside function, and we can take the derivative of it first. We just use the chain rule as usual, but we can ignore the function inside the brackets for now. Once we get the derivative of the outside, we have to multiply that by the derivative of the inside function. And after putting these pieces together, this is what the derivative will look like. Using the chain rule can get really hard when taking the derivative of a function inside a function inside a function, and so on. So organization is key here.
Second derivative? There's another one? Well, maybe it's not so scary now that you've taught me the first derivative, senpai.
Anyways, yeah, there is a second derivative. Algebraically, it's just taking the derivative of the derivative, which should be easy by this point. The hard part is understanding what it means, so let's first clarify that. The first derivative represents the slope of the tangent line at any point, or the IRC. This shows us when and how fast the original function increases or decreases. Now onto the second derivative. Of course we would simply use the power rule to differentiate the first derivative. And now we have this.
But what do these numbers mean, senpai?
Let's introduce another new term, concavity. Concavity is just the way a function curves, that being either concave up, a smile, or concave down, a frown. We can see that the second derivative of x squared is a constant value. This means that the original function is constantly concave up because it's positive, and it would be constantly concave down if it was negative. Now let's look at x cubed. Just by looking at this function, we can see that there are two different concavities, one part going up and the other going down. Let's take the second derivative of this and see what happens. The second derivative comes out to be 6x, which is a linear function as opposed to the constant value from earlier. When this line is positive, the original function is concave up, and when it's negative, the original function is concave down.
But senpai, what if the second derivative is 0?
Okay, you can stop talking like that now. But yeah, unfortunately that is a good question. I'll use a linear function to help explain this. The first derivative of 2x is a constant, so what happens next? Well, we know that the derivative of a constant is just 0, but what does this mean? When the second derivative is 0, it's neither positive or negative, obviously. Therefore, the concavity is neither concave up nor concave down. This means that 2x has no concavity. This function here was used to make Miku's lashes. It makes a funny shape, so let's use it to better understand slope and concavity. First, let's identify the intervals of increase and decrease. There are intervals of increase whenever the slope is positive, and wherever it's negative, there's an interval of decrease. So I'll highlight those areas. What about these points though? The slope is 0 here, so what do we do with them? This point here is called a local maximum, and this one is called a local minimum. This point doesn't have a special name though, since it's not a max or min. Now I'll do the same thing for concavity. Where is this function concave up? Well, we can clearly see that it smiles at the ends here. But at what point does the smile end? At first you might think it ends up here, but it's actually concave down there. So where does it switch from up to down? The answer is right here, at the straightest point. This is called the point of inflection. The concavity is 0 at this point because it's straight here. Optimization is just the process of finding local maximums and minimums, also known as extreme values, of a function. We can easily do this for quadratics, but for more complicated things we'll have to use calculus. Which points here look like the local maximums and minimums? Well, this point here is a local minimum, and it's also the global minimum, meaning it's the lowest point in the entire function. The local maximum of this function would be infinity since it just keeps going up. So how do we find the max and mins when we don't know what the function looks like? It's actually really simple. All you have to do is evaluate the function wherever the derivative is 0. And if there are any domain restrictions, then evaluate the function at those points too. Whatever the highest and lowest values of those points are the maximum and minimum values. I'll use Miku's leg as an example for this. Well, we already do know what the function looks like, but let's prove what the mins and maxes are. If we restrict this function to this domain, there are less extreme values, but what are they? Let's check using the derivative. First we have to expand the function so we can take the derivative of it. Now, we set the derivative to 0. This will give us the x values of the extreme values, but not the points on the original function. To find the actual points, we can plug in these x values into the original function to get the points of our extreme values. Next, we have to check out what the function is at the boundaries, just in case there is a maximum or minimum value at those points. Out of the points we found, the highest value is 4.66, and the lowest is 3.58. These are the maximum and minimum values within this domain. So yeah, that's the video.